In this video, we're going to learn about the addition rule and complements for probabilities. So starting with the addition rule for disjoint events. Two events are disjoint if they have no outcomes in common. Another name for this is mutually exclusive events. So let's take a look at this example. We draw Venn diagrams a lot of the times when we're looking at our probabilities and our events. So this picture represents the events as circles enclosed in a rectangle. So the rectangle here is equally as important as the circles. The rectangle represents our sample space, and each of the circles represents an event. So for example, let's say we randomly select chips from a bag where each chip is numbered or labeled with the numbers 0 through 9. So we're going to say that the event E is where we choose a number less than or equal to 2. And then we're going to let the event F be where we choose a number greater than or equal to 8. So notice that these two events are disjoint or mutually exclusive. You can tell visually, and then also just by knowing what we have as far as our outcomes in our bag. Choosing a number less than or equal to 2 has no common outcomes with numbers greater than or equal to 8. And so the numbers that don't fit into either one of these events, notice they're still represented in the rectangle for our sample space. Okay, so remember this notation. This says the probability of event E, and we can compute it using our empirical method as the number of outcomes for our event divided by the number of outcomes of our sample space. So our denominator is 10 because there's 10 numbers that we could choose from, and then the probability of, or the number of outcomes in our event, numbers 2 or less, is 3 numbers. And so the probability of this occurring is 0.3 or 30%. Similar calculations for the probability of numbers 8 or greater would be 0.2 or 20%. And so if we wanted to calculate the probability of event E or event F, then what we could do is we can say that that's the number of outcomes in either event divided by the number of outcomes in our sample space, giving us 0.5 or 50%. But we can actually do this another way. This is equal to the probability of event E plus the probability of event F. So notice we get the same answer of 0.5 by just adding up the two separate probabilities. And this is possible because the two events are mutually exclusive or disjoint. So this is an example of the addition rule for disjoint events. Anytime your events are disjoint or mutually exclusive, then the probability of one or the other is just the addition of the two individual probabilities. So the addition rule for disjoint events can be extended to more than two disjoint events if we need to. So in general, let's say we just had events E, F, G, and so on. As long as they're all pairwise disjoint or mutually exclusive, then the probability of E or F or G or so on is just the sum of the individual probabilities. Okay, so we're just going to add in an event. We're going to say G represents the numbers 5 or 6. And so now we had calculated the probability of a number less than 2 or less, and that was 0.3. The probability of a number 8 or greater was 0.2. And now the probability of the number 5 or 6, which we're calling event G, is 2 out of 10, so 0.2 as well. So then if we wanted to calculate the probability of event E or F or G, we can use our addition rule and add up the individual probabilities, just 0.3, 0.2, and 0.2 for a total of 0.7. So this is basically saying 70% of our outcomes will have either 0, 1, or 2, 5 or 6, or 8 or 9 in them. Now let's take a look at this example. So our number system consists of the digits 0 through 9. Because we don't write numbers such as 12 as 0, 1, 2, the first significant digit in any number must be between 1 through 9. You may think that each digit appears with equal frequency as the first digit, so that each digit has a probability of 1/9 of being the first significant digit, but this is actually not true. So in 1881, Simon Newcomb discovered that digits do not occur with equal frequency in the first digit position. and then the physicist Frank Benford discovered the same result in 1938. So after studying lots of data, he assigned probabilities of occurrence for each of the first digits, and we have those results here in our table. The probability model is now known as Benford's law, and it actually plays a major role in identifying fraudulent data on tax returns and accounting books. So if we just take a quick look at our table, notice that the probability of 1 being the first digit is the highest out of all the numbers. So we're going to first verify that Benford's law is a probability model. So we've talked about a probability model before. It has to list the outcomes and their probabilities, and it also has to satisfy our rules of probability. So each probability in our table is between 0 and 1. If you recall, that was one of our probability rules. And then also, the sum of all the probabilities, if we add them up, is 1. And that was our second probability rule. So because both of our rules are satisfied, this table represents a probability model. So now we're going to use Benford's law to determine the probability that a randomly selected first digit is the number 1 or 2. So we can use our addition rule for disjoint events and take the individual probabilities of the first digit being 1 and add it to the probability of the first digit being 2. So we get a total of about 47.7%. So if we looked at 100 numbers, we would expect about 48 of those numbers to begin with the numbers 1 or 2. Now let's use Benford's law to determine the probability that a randomly selected first digit is at least 6. So what I want you to notice is to find the probability of at least something, we take that number and anything greater. So we actually want the probability of 6 plus 7 plus 8 plus 9. We add up those 4 individual probabilities to get that 22.2%. So if we looked at 100 numbers, we would expect about 22 of them to begin with either a 6, 7, 8, or 9. Okay, so now let's try this example. We're going to suppose that a single card is selected from a standard 52 card deck, which here is a standard 52 card deck where we have aces through kings and then our 4 suits. So we're going to compute the probability of the event drawing a king. So our sample space is our 52 cards. And a standard deck has 4 kings in it. So the number of outcomes of our event is 4. Therefore, the probability of drawing a king, if we use our empirical method, it's the number of outcomes of our event divided by the number of outcomes in our sample space, which is just 4 out of 52. Or we can simplify that and say that it's 1/13. Now let's compute the probability of the event drawing a king or drawing a queen or drawing a jack. So a standard deck has 4 kings, 4 queens, and 4 jacks. Each of these events are mutually exclusive or disjoint, and so we're going to use our addition rule for disjoint events, and we're just extending it to 2 or more disjoint events. And so our probability of king or queen or jack, we can use our rule for disjoint events and say that it's the individual probability for drawing a king plus the probability for drawing a queen plus the probability for drawing a jack, which each of those is 4 out of 52, which will give us 12 out of 52, which you can simplify to 3/13. All right, now we're going to use the general addition rule. And this rule is going to be used for when our events are not mutually exclusive or disjoint. So let's let E represent the event to choose an odd number, and let F represent the event to choose a number less than or equal to 4. And this was from when we had a bag of chips with the digits 0 through 9 on them. So notice what we have here with our Venn diagram. An odd number is in our circle for E. It could be 1, 3, 5, 7, or 9. And then our numbers less than or equal to 4 is in our purple circle here for F. And it could be 0, 1, 2, 3, or 4. And so we do have an overlap of the 2 events, so they are not mutually exclusive. the overlapping region, we call it E and F. So the and part is what makes it the overlap. And then together, E or F is basically all of the two circles. So the probability of E or F, in other words, the probability of choosing an odd number or choosing a number less than or equal to 4, we have to use a different rule to account for the overlap. So notice it's similar to our rule for disjoint events. It's the probability of our first event plus the probability of our second event, but there's an overlap, so we actually account for that by subtracting. So minus the probability of the overlap, which is called E and F. And so we know for choosing an odd number, that's 5 out of 10. Choosing a number 4 or less is 5 out of 10 as well. And then those two events overlap with two numbers, so we subtract 2 out of 10 for a total simplified of 4/5 probability. So now let's just verify this by doing the same computation but by hand. So this down here was using our general rule of addition. And by hand, if we just kind of look at it, the probability of event E or F, there's 8 out of our 10 numbers for those events. And so that's also 4/5. So we get the same result. So notice that this is not what we get if we were to use our addition rule for disjoint events. In that case, the probability would have actually been 1, which is incorrect. So our general rule for addition is for any two events, the probability of event E or F is the sum of the individual probabilities minus the probability of the overlap, E and F. And so you can actually use this rule for disjoint sets as well, because the probability that they overlap would be 0. So you would pretty much just be subtracting 0 here. So this is our general addition rule. So let's take a look at this example. Suppose a single card is selected from a standard 52 card deck. We're going to compute the probability of the event that we're drawing a king or that we're drawing a diamond. Okay, and so using our general addition rule, we're going to add individually the probability of drawing a king plus the probability of drawing a diamond, but then we have to subtract the overlap, which would be the probability of drawing the king of diamonds card. Okay, so we have 4 out of 52 would give us the kings, 13 out of the 52 cards are diamonds, and then out of all 52 cards, only one of them is the king of diamonds. So we would get a probability of drawing a king or a diamond as 4 out of 13. Okay, let's take a look at this one. This data shows the marital status of males and females 15 years or older in the US in 2017. So notice what we have. We have some rows telling us about the marital status, and then we have columns telling us about male or female. So we've seen these in the past, but this is a contingency table. Sometimes it's called a two-way table, and it's because it relates two categories of data. The row variable in our case is the marital status. It makes up the rows of our table, and then the column variable is the gender. And then each cell each box is a cell. So we're going to use that table to answer the following. We're going to determine the probability that a randomly selected U.S. resident, 15 years or older, is male, that they're widowed or divorced, and then that they're male or widowed. Okay, so first what we're going to do is we're going to get some totals. So if we add the entries of each column, for example, if we add the entries from the male column, just adding straight down, we would get that the total number of males would be 126.9 million. So we could put that down here at the bottom. If we add all the entries of our rows, we would have the totals over here to the right. And so for example, for never married, we would add the males and females, and we would get the 86.1 million residents were never married. Okay, so we can add all the row totals and all the column totals, and they should equal. Okay, and that would go in like the bottom right corner, because that's how many people are in included in this data. So if we add all the rows, all the columns, in either situation we'll get 260.1 million residents. All right, so for part A, 126.9 million males of 15 years or older out of the 260.1 million residents. And so what we want to do is we want to get that proportion or probability. So the probability that a randomly selected U.S. resident is male is just the 126.9 divided by the total, 260.1. So it's about 48.8%. Part B, there's 15.2 million residents that are widowed, and so the probability that a randomly selected resident is a widower would be the 15.2 divided by the total, which is about 5.8%. Part C, the events widowed and divorced are disjoint. And so we use the addition rule for disjoint events. So we just add up the individual probabilities of widowed and divorced. And so we have a total of about 16.7%. And then for part D, the events male and widowed are not disjoint or not mutually exclusive. Someone can be both male and widowed. So in fact, there's actually 3.3 million males who are widowed in the United States. So this time we have to use our general addition rule because they are not disjoint events. So we're going to take the individual probability of male, add the individual probability of widowed, and then subtract the overlap of male and widowed. And so after we do that, so we get that about 53.4% are male or widowed. All right, next let's compute the probability of an event using the complement rule. So the complement of an event, we let S denote the sample space of our probability experiment. E denotes our event. We've used those notations in the past. And so the complement of E, we denote it as E with this little superscript of C, is all the outcomes in the sample space that are not outcomes in the event E. So basically everything that's not part of the event E is its complement. And so the complement rule says the following: if E represents any event and E complement represents a complement of E, then the probability of the complement of the event is 1 minus the probability of the event. So the reason why this makes sense is because total probability for all the outcomes is 100%, or 1. And so if the probability, whatever the probability of our event is, everything else, which we call the complement, together they have to add up to 1. So that's why if we, let's say you just add over here, say plus probability of E, together they would equal 1. All right, so just a visual for you. If E is the circle, represents our event, then everything else in our rectangle is what we call the complement of E. And together it makes up the whole region. So for this example, according to the National Gambling Impact Study Commission, 52% of Americans have played state lotteries. What's the probability that a randomly selected American has not played a state lottery? So the probability that an American has not played a state lottery, because we don't know that probability, we know its complement, we can use our complement rule and say 1 minus the probability of Americans who have played. And so we say 1 minus 0.52, and so we get that 48% of Americans have not played a state lottery. Now let's take a look at this one. This data shows the income distribution of households in the United States in 2017. So we have our annual income all the way from less than 10,000 up to 200,000 or more, and then the number of people in the United States represented in thousands. So we're going to compute the probability that a randomly selected household earned the following income amounts. So 200,000 or more. Okay, so there was a total of 7,804. Remember, these are all in thousands, plus 5,403, and so on. It was a total of 120,063 times 1,000 households in the United States if we just add up all of our values in our numbers column. And so of them, the people that earned 200,000 or more was the very last cell on the right, which was 8,284. Remember, that's times 1,000. Out of our total number of people, so that's about 6.9%. And so the probability of randomly selecting a household that earned $200,000 or more in 2017 was about 6.9%. Another way to say that is if we randomly selected 1,000 households, about 69 of them would have this income. Now let's calculate the probability of less than 200,000. So we could do this by adding the relative frequencies of each of the categories less than 200,000, but there was quite a few categories to do that with, so there's actually a way easier way to do it, which would be to use the complement. Since only one of the cells was dealing with $200,000 or more, then we can just take the complement of pretty much what we just did. And so the probability of less than 200,000 is just 1 minus the probability of 200,000 or more, which we just figured out was 0.069. And so the probability of earning $200,000 or less than $200,000 was about 93.1%. And so another way to say this is if we randomly selected 1,000 households, we could expect 931 of them to have household incomes less than 200,000. All right, now let's compute incomes of at least 10,000. So at least 10,000 means greater than or equal to, so we need to be careful about that. And so what we could do is we could add up, find all the relative frequencies and add all them up for all the other categories other than the first one, which was less than 10,000. But the faster way, again, is going to be to use the complement. So the complement of at least 10,000 is less than 10,000. Because remember, this means 10,000 or more. So its complement is less than 10,000. So in 2017, we had 7,804 times 1,000 households earned less than 10,000. And so using the complement rule, the probability of randomly selecting a household that earned at least 10,000 is 1 minus the probability of selecting a household that earned less than 10,000. So 1 minus 7,804 over our total, which is 93.5%. So the other way to say this is if we selected 1,000 households, we could expect that 935 of them had incomes of at least 10,000. All right, that's it for this one. Thanks for watching.